Have you ever wondered, how does a massive block of steel weighing hundreds of thousands of tons float in the middle of the ocean? A ship that is more than 400 meters long, as tall as a multi-story building. Inside, it carries thousands of containers, millions of liters of fuel, and machines weighing thousands of tons. But strangely, it remains calmly on the surface of the water. Meanwhile, just a small iron ball or a simple metal bar dropped into the sea will sink straight to the bottom. So what is really happening? Why can steel, a material famous for being heavier than water, become the foundation of the largest ships ever created by humans? The answer is not that steel becomes lighter. It lies in an ancient law of physics, a law that has existed for more than 2,000 years. And it is this law that has allowed humans to transform massive blocks of metal into floating cities in the middle of the open sea. For thousands of years of history, humans only knew one simple truth: wood floats, iron sinks. The first boats were created from tree trunks. Later, humans hollowed out wood, joined multiple pieces together, and created vessels capable of crossing rivers and oceans. Wood was the perfect material. It was lightweight, easy to shape, and most importantly, it could float. But as civilization developed, humans wanted to travel farther. They wanted to transport more goods. They wanted to create stronger ships. And wood began to reveal its limitations. A ship that was too large required thousands of pieces of wood. It could rot over time. It could burn during battles. And it was not strong enough to withstand the new demands of the maritime industry. Humans needed another material, stronger, more durable, and the answer seemed obvious: metal. But immediately, a problem appeared. Everyone knew that metal sinks. If you hold a piece of iron and drop it into water, it will disappear within just a few seconds. Therefore, the idea of building a ship out of iron was once considered completely insane. A ship made of metal? How could it possibly float? It would sink the moment it left the shore. But some engineers began asking a different question. Does the material itself really determine everything? Or is the way we shape and create that material what truly matters? In 1787, an English engineer named John Wilkinson decided to prove what many people believed was impossible. He built a barge made entirely of iron. When the vessel was launched into the River Severn, a large crowd gathered to watch. They waited for the moment when the massive metal ship would sink. But a few seconds passed. It was still floating. A minute passed. It was still on the surface. And then the ship began to move. This forced the entire world to reconsider. It turned out, iron does not automatically sink just because it is iron. The secret lies in the shape. Imagine a flat sheet of steel. You throw it into the water, it sinks. But if you take that same sheet of steel, bend it into the shape of a bowl, it floats again. What has changed? Not the material, not the weight, but the space inside. A bowl contains air, and that air completely changes the way water interacts with the object. A ship works according to the same principle. It is not a solid block of steel. It is a massive steel shell surrounding a space filled with air, and that space is what creates the difference. More than 2,000 years ago, the Greek scientist Archimedes discovered an important law. An object submerged in a fluid experiences an upward force. That force is equal to the weight of the fluid displaced by the object. Simply put, water always tries to push an object out of the space it occupies. When a ship enters the ocean, it takes up a huge amount of space. It pushes a massive amount of water away, and the water pushes back against the ship. If the upward force is strong enough, the ship will float. This is why a steel ship weighing hundreds of thousands of tons can still remain on the surface of the ocean, because water does not care what the ship is made of: wood, iron, or steel. What truly matters is the average density of the entire ship. A solid block of steel has a density greater than water. it sinks. But a massive steel structure filled with air has an average density lower than water, and it floats. But a ship does not only need to float, it must also remain stable, because the ocean is never completely still. Waves dozens of meters high can affect a ship weighing thousands of tons. That is why inside every modern ship is a complex system: watertight compartments, ballast tanks, weight control systems. When a ship is too light, it floats too high and becomes easier to lose balance. The crew pumps seawater into the ballast tanks. The ship becomes heavier. It lowers deeper into the water and becomes more stable. When the ship is carrying a full load, the water is pumped back out. Everything is calculated precisely down to the smallest detail. This principle is also applied to one of the most mysterious machines beneath the ocean: submarines. A submarine can decide its own fate. Want to sink? It allows water to enter the tanks. Its weight increases. It dives downward. Want to rise? It uses compressed air to force the water out. Its density decreases, and it returns to the surface. Once humans understood this principle, they began building ships that had never existed in history before. Massive oil tankers hundreds of meters long. Giant container ships are capable of carrying tens of thousands of containers in a single journey. Ships so large that if placed on land, they would look like horizontal skyscrapers. But in the middle of the ocean, they are still simply objects being supported by water. However, the ocean always has a way of reminding humans that everything has its limits. On April 14, 1912, one of the most famous ships in history was traveling across the North Atlantic: Titanic. It was considered a masterpiece of engineering, a modern ship, a symbol of human confidence. But when it collided with an iceberg, a chain of unexpected events began to unfold. Water started flooding into multiple compartments. The ship gradually lost its ability to maintain balance, and finally, it sank to the bottom of the ocean. That disaster changed the shipbuilding industry forever. Humans realized that physics never fails. But every design has its limits. No matter how advanced a ship may be, it must still respect the power of nature. So, how large can a ship become? In theory, there is almost no absolute limit. A ship stretching an entire kilometer in length could still float, as long as its average density is lower than that of water. But the problem is no longer whether it can float. The real challenge lies in structural strength. Waves constantly bend the body of a ship. Metal can experience fatigue. Ports have limitations. Canals have limitations. Operating costs also have limitations. In the end, giant steel ships do not float because steel is lighter than water. Steel is still heavy. It can still sink. But humans have learned how to transform it into a structure filled with air. A simple idea, a natural law, yet powerful enough to change the entire course of civilization. Today, most of the world's goods are still transported across the oceans. Every car, every smartphone, every item we use may have once been carried on a massive steel ship in the middle of the sea. And all of this exists thanks to something that seems incredibly simple: understanding how water supports an object. That is the power of science, not defeating nature, but learning how to work together with it.